We have a partition of the vertices except the leaves. On a tree, you also have the set of leaves, which I denote by L. And this represents, okay, I will come back to the interpretation. This set omega represent where, or omega I represent where the player I has to take a decision. But then we have a subpartition of this set omega 1 up to omega n in terms of small omega ij. And I made a picture of this. It's a subpartition of this set, the set of all vertices, but not the leaves or not the nature. And these set omega ij are called also information set. And altogether, they form an information partition. It's a partition of this set. Then we have also something about edges. We have in the definition a C, which is also a partition of all edges except those starting at omega 0. Omega 0 is the nature. And it's called the choice partition. And I explained precisely what it means last week. We also have, now it's related to nature, at each point x belonging to the omega 0, so the nature, we have a probability distribution on each edge. And finally, we have U, which is a payoff, which is defined on the leaves. And as I mentioned here, there are conditions on this set omega ij and also on this set Cijk, which I don't recall. But yeah, we did a picture last week and we tried to explain everything. And just for information, if you take the path from the root of the tree, which I usually denote by x0, to any leaves, it's called a play of the game. So this is a unique path from the root to a leaf. So this was a description of an extensive form game. You need all this. And then I mentioned what means if the game has perfect or imperfect information, which is still rather simple. The notion of perfect or imperfect recall is a bit more subtle, but most of the time we assume that we have a perfect recall. So if you're not sure, check the notes. And then I introduced strategies. So there is a set of pure strategy which put a 0 or 1 on each edge. And then you have what is called behavior strategy, which is when you put some probability of going in on one edge. So you need to distribute some probabilities. And it turns out that the set of pure strategy is inside the set of behavior strategy because these are just special cases. But once you have put a behavior strategy, it means you have your tree. Once you have decided about a strategy or a strategy profile, I should write, sorry, pure strategy profile, it would be better. And because A is made of, any element of A has n components. So this is a strategy, a pure strategy for player 1 up to player n, and altogether there are strategy profile, and the set A is made of all strategy profiles. And the same B is made of all behavior strategy profiles. But once you have such a tree and put a strategy profile which put a certain number on all edges, you can take an x and compute the probability that you go from x0 to x with this strategy. And I gave a formula, it's just a multiplication of what you have before between the root and x. And it gives you the probability that players go through x when playing this strategy. And if you just look at leaves, these numbers define a probability on the set of leaves. So it means if you sum these p x b on all leaves, you end up with 1. And with this probability distribution on the set of leaves, you can now give a weight or payoff for a strategy for the player I by this formula. So you do the sum on all leaves, take this distribution, because as I said, it's a distribution on the set of leaves, and you multiply by the payoff, which was in the initial definition. So if you're not sure about all this, look at the notes or look at the picture I did last week. And this is a payoff for the strategy B. Okay. So an extensive form game is not a simple object, but if you draw some examples, you can easily see what it is. Any question or remark? So today we are going to study these strategies and also Nash equilibrium on such games. So what is important to remember is that this set of pure strategy is inside B, and that this set is finite. Yes, last week I even counted on an example how many elements we have in A. It's a finite number. While this is not finite because you put some probabilities, so it means you put numbers between 0 and 1, it can never be finite. But the set of pure strategy is finite. And that this formula, which is valid for any B inside this set of behavior strategy, is also valid for any A in this set of pure strategy, because A is included in B. So I'm going to use this not for B, but for A. Because now, so it's an observation, and then I give a new definition. A, which is a set of pure strategy profiles, is finite. And it's made of A1 times A2, or I should write the product notation. It's A1 times A2 up to AN, because you have each element has n components. Each element in A is made of the pure strategy for the first player, the pure strategy for the second one, and up to the pure strategy to the last one. So we have this set which is finite and which is made of strategies for each player. And we have, if I use this formula for A instead of B, we have a payoff on UI defines a payoff function or utility function on any A belonging to A. So if you think like this, we are back to the framework of the previous section or the previous chapter. So I'm going now to define a strategic game like in chapter 2. So this is a new definition, which is a bit confusing, but not so much. So for any extensive form game, which I denote just by gamma, the finite n players game defined by A and this blue utility function is a strategic game. Denoted by, so if I use G of gamma. So it means starting from an extensive form game, I can define what we have seen in the previous chapter, which is this set of strategies and a utility function or a payoff function. And you can do one more step, because this is finite. So what we did when it's finite, we can even construct the mixed extension. So the mixed extension of G gamma is denoted by, if I use the notation of the previous chapter, I should just call it E of this G gamma. And remember, it's made of two things. It's made of P, and now red U, I used the red in the past. P is a set of probability distribution on A with a very precise definition, and U is a utility function which is defined with this U. So if you just look back, we define everything in chapter 2. So you end up with 3 objects, and then you can wonder what are the relations between them. I encourage you to draw a small, I encourage you, you just do a game quite simple. And each of these things has a meaning. Then you put some colors. Probably I should make it more complicated. Then you put some colors. And there are examples in the notes. This is a game like I introduced last week. And you can try to write or exercise on an example or on a few examples. Write what is this game, and in particular, what are pure and mixed strategies, and behavior strategies. What is also write what means G of gamma and describe mixed strategies. It looks complicated, and it will take you 1 hour just to digest this information. But if you do it, you are going to learn a lot, because you will see that pure strategies is simply putting some 1 on 0 and 1, 0, and so on. This gives you a pure strategy. It's made of 0 and 1. At each vertex, the sum should be 1. Then a behavior strategy, you put some probability, okay, which can be any number between 0 and 1, but again, they have to sum up to 1. So if you describe this, you get the set of all behavior strategies. Then this guy is again made of pure strategies, so you will not see something very different. But then mixed strategies are something different. Mixed strategies is you take a combination of pure strategies, which is not the same as putting arbitrary probabilities on these edges. So I really encourage you to spend or to write a few examples and see what are these different objects. It's not difficult, but you need to look at the definition. So draw one example, write what are pure strategies, what are behavior strategies, and what are now mixed strategies. I would be happy to see a few examples. But then you can wonder, oh, is there any relation between mixed strategies and behavior strategies? At the end, you are going to end up with numbers on edges, but can you identify these two things? So this is a question, a natural question. What is the relation between behavior strategies and mixed strategies? So the first answer would be, oh, essentially the same, because for behavior strategies, you put some probability distribution like this. Then for mixed strategies, you take a picture like this with only 0 and 1, and you do some probability on these graphs, on pure strategies. Unfortunately, or fortunately, no, it's not exactly the same. And in order to see the difference, so for understanding the difference, we need to extend one definition. It took me a while to understand because nobody explained really that they extend it. Let me tell you the details. What we have seen, we know what is P of X B. It is a probability of reaching X if you follow the strategy, the behavior strategy given by B. So as I said last time, you have numbers everywhere. And if you take this X, you're going to associate a number to each point. This is what I said. But in fact, we can also define P of X, and I'm going to use another letter, sigma. No, I can, let me put another P. With P, P1, Pn. I will explain Pi is. This part is just a bit confusing. So remember, a mixed strategy is a probability distribution on this AI. And I denote it by P. So you have a probability distribution on the set of pure strategy for the first player, probability distribution for the pure strategies of the second player, and so on. I use P. But this P, it also defines numbers between 0 and 1, between 0 and 1 on each edge. If you just look at the definition, you will see that you are again going to put numbers on each edge with this, which is a mixed strategy. It's a mixed strategy profile. So it means there is a clash of notation. Okay, we have too many P. I define this, and now, okay, let me use a different color. Yeah. Sorry. No, there is a difference because this P needs two arguments. Here I have no argument, but still it's better to use a different color. So we have defined this probability of reaching X if you follow the strategy B. This B is a behavior strategy. Now, if I construct the mixed extension, we have seen that we have what I denote by P, with Pi a distribution on the set AI, which is now the set of pure strategies. But if you look carefully, this also defines, in fact, a number on each edge. So I can do the same game. Once I have numbers on all edges, I can just compute the probability of reaching X with these numbers. So it means I will use this notation for two things. Because at the end of the day, you do the same thing with two slightly different approaches. So we can also define P of X and now P. Yes. Okay, which one? The second one is blue. Thank you. And I write it again. It's meaningful. It's a probability of reaching X if you have a mix. This one is a mixed strategy profile. While here it was a behavior strategy profile. But at the end of the day, you get the same thing. You get numbers on edges, and you can just count the probability of reaching X by multiplying these numbers. So it means I'm going to we use the same notation here and here. We use now P of X and sigma for sigma is equal either to B or sigma is this P. So I'm going to use the same notation for two things which are slightly different, but at the end of the day, they just give me some numbers I can associate to any X. I look at many books, nobody is doing this very nicely. They always hide something and use the same notation for two slightly different objects. But is there any question? Again, I encourage you to do the exercise I mentioned before, because if you do it, you just see what you're doing by yourself. So now I have this notation both for behavior strategies and for mixed strategies. So I can give a definition and then a rather important result. So it's a definition. In this framework, so I mean in what I have introduced up to now. A strategy, behavior strategy, and a mixed strategy are called realization equivalent if for any, I will explain, but And somebody will complain I should put colors. This is a PI. This is a blue PI. And yes, that's it. So what does it mean? It simply means so as I said, they are not exactly the same object. This BI and this PI, if you look at the precise definitions, they are not exactly the same thing, but they put numbers on edges. So this is the only thing you should really take care of. And we say that they are realization equivalent if when you take here BI, or if you take PI, and all the other things are the same, you get the same numbers. That's it. So if you use the first line with a behavior strategy, or if you use the second line with a mixed strategy, you don't see the difference on the numbers. That's the meaning of this definition. We call this realization equivalent. I cannot write, be careful, I cannot write BI equal to PI. This is not allowed because if you look carefully, they are not the same object. So this wouldn't be correct, but when you look at the numbers they generate, these definitions say they generate the same numbers. Okay. So this is not correct. Not correct. Because they are not the same objects. And now I introduce this for an important result, which is called Kuhn theorem. So remember my initial question was, oh, we have mixed behaviors, we have strategic behaviors. We have mixed behavior and, mixed strategies and behavior strategies. Are they the same? That was my original question. And this theorem tells you the answer. If gamma has perfect recall, and try to remember, it was a rather subtle condition last week, but I told you in most of the examples we impose it. If gamma has perfect recall, any BI in the behavior strategies is a realization equivalent to PI, which is mixed strategies, and vice versa. So this theorem helps you. Because it tells you that under a rather natural condition, you can either play with mixed strategies or you can play with behavior strategies, and you don't lose anything by choosing one of them. So any BI corresponds to a blue PI, and any blue PI corresponds to one BI in the sense I mentioned. Okay. Again, I cannot write an equality, but you have to, if you remember, you have a one-to-one bijective relation. So any BI define a unique PI, and any PI define a unique BI. This is the way you should think about it. And this is good for you for the following reason. Look, when we discuss mixed strategies, we said when you have a mixed extension, there are algorithms for finding a solution, an optimal strategy. So if you are in this framework, you can use again the same formalism. You have algorithm for finding the best strategy or the optimal strategies. So once it means you have two slightly different framework, but you can use, if this assumption is satisfied, you can use the tools developed for both. So this is good point. However, there is one thing which I observe. Be careful, and we already mentioned it last week. The set A can be rather large. Why I write just this? Because if you use an algorithm for finding the best strategy or the optimal strategy, you may have to deal with a set A, which is already quite big. So yeah, you are in a vector space of big dimension. That's just a remark. So I encourage you also, if you're interested in this, you can either look at the proof. It's not completely trivial, but it's not so difficult. And look at examples. And what I mean by an example, there are easy graphs which do not satisfy this. If you look at the definition, it's easy to find a graph which do not satisfy this. And then if it does not satisfy this, it means if you look at all behavior strategies and all mixed strategies, you cannot do this one-to-one correspondence. So there are a few exercises about this. Okay, that's all for this section. Now let's move to equilibrium. But we will use this theorem in the future. Equilibrium in extensive form game. So we defined Nash equilibrium in strategic games. And we want to do the same here. And the first definition is essentially the same. So for an extensive form game gamma, a behavior strategy remember, I use the letter B if it is behavior strategy profile. B star. I use a star for this specific one. So this one is a Nash equilibrium. If, and in fact, you can write the definition by yourself because we have all the ingredients. So it's if for any I, for any player, what we have, and any bi in bi or bj, no, bi. What we have that the utility, which is a blue one, the utility I of B1 star up to Bn star is bigger or equal to this utility for B1 star up to Bn I minus 1 star Bi plus 1 star up to Bn star. And you observe this is the same definition as before in the strategic game. It means you want, so here we have only stars. On the right-hand side, I just change one with a non-star, and we want that the star is bigger for this utility function for the I1. So it's exactly the same definition as for strategic game. But you can already see one thing. Oh, in strategic game, we had no dynamic. It was just you choose the best strategy and all players choose once the best strategy. Now we are in these trees and you want to have a dynamic. On trees, the game is moving on this tree. This definition doesn't take care of this. So it means it's not going to be a perfect definition. We will do something better, which takes the dynamic into account. This is very static. It gives you the Nash equilibrium, so it gives you the set of all Nash equilibrium. But in fact, we will look at smaller set inside because they are better. But yeah, these points which are Nash equilibrium gives you the best payoff in a very precise sense. So it means Ui has no interest of moving away from Bi star because he would lower his payoff. Okay. So this is the definition of a Nash equilibrium. But let me just remark, I said it, but this definition does not take the dynamic. It's not a precise remark, but we will make it a bit better later into account. However, we have already a small result. By Kuhn's theorem, we can already say something. Remember, for mixed extension, we always have a Nash equilibrium. This was a statement for strategic games. So it means if I have a one-to-one correspondence between behavior strategies and mixed strategies, I can use the previous result. So it's a theorem. And if gamma has perfect recall, which is what I need for this one-to-one correspondence, then they exist at least one Nash equilibrium. And this is something it's not really necessary to prove it because we already know it. We know this result for mixed behaviors, for mixed strategies. And if we have perfect recall, there is a one-to-one correspondence. And since the definition is the same, we get it. That's it. So we know that if we have perfect recall, there exists at least one Nash equilibrium, and we can say even a bit more. Can say a bit more in the following sense. If B star is a Nash equilibrium for gamma, then it's uniquely defined. A Nash equilibrium for E of. So what does it mean? And observe that here I didn't take the assumption that it's a perfect recall. I am just saying if you have a Nash equilibrium for gamma, I'm not asking for perfect recall, so I'm not asking for this additional condition, then it defines a Nash equilibrium for this mixed extension. But now you can already suspect something. The converse cannot be true. The converse cannot be true because if it were true, then I wouldn't need this condition. So, but be careful. If no perfect recall, a Nash equilibrium of the mixed extension and we know it exists. But this Nash equilibrium does not produce something for gamma. So if no perfect recall, a Nash equilibrium for this does not produce or generate Nash equilibrium. And this is clear, because if not, then I wouldn't need this additional condition. There would be a contradiction in what I'm writing on the blackboard. If any Nash equilibrium of the mixed extension would generate a Nash equilibrium for gamma, then I wouldn't need this. So it means this condition, which is annoying, makes that a Nash equilibrium for a mixed extension do not create a Nash equilibrium for the extensive form game. Okay. That's quite natural. So in particular, not all gamma have a Nash equilibrium. And you can find in the literature some easy example where you don't have a Nash equilibrium. Of course, it means that the graph has not a perfect recall. So you have to check this assumption.
Professor?
Yes.
You have in the theorem that if gamma has perfect recall, then there exists at least one Nash equilibrium. So if there are two Nash equilibrium, for example, and does that mean there are two mixed extensions?
I don't know. I cannot answer this. We always state the thing, there exists at least one. Now, if you have more than one, you are probably lucky, but I cannot tell you if it's a one-to-one correspondence when you have perfect recall. So yes, probably it means if one of them has two, the other one has also two when you have perfect recall.
Okay, thank you.
Welcome. Any other question? Again, please think about report. You should take this opportunity. It's easy to do a report on a small graph like this with some property. It's not so difficult. And already if you study these kind of things, maybe with some, you need some information set which are not trivial, otherwise perfect recall will always be satisfied. So you need some information set containing more than one point. But it's easy to generate examples which show either, which illustrate either a theorem or show a counterexample. Okay. I decided to spend again a few minutes on one example. Even though any example take a lot of time for me, because I have to introduce a lot of things, but sometimes it's good to work on one example. So let's work on one example. I don't, in the notes, I refer to a text, but here I just draw the corresponding graph. So this is, there are two players. And we have payoff function 0 alpha beta -1 -1 beta 0. And this is called omega 1. This one. So this is a leaf, this is a leaf, this is a leaf, and this one is omega 2. And the edges have a name. I just take the name from the book. There is an interpretation. So there is a story about this graph, but you can just take it as a graph. But if you look at the text, there is a meaning for this name. So how many pure strategies? I told you, you really need to go on one easy example to really understand what happens. Pure strategies is you put 0 or 1. So it means we have 4 pure strategies, and I'm going to denote them like this, and we will see why. Y, and then E, F. This is just a notation, but it gives us these 4. What does it mean? It means I put a 1 on this edge. O, it's a O, it's not a 0, sorry. I put 1 on this edge. I need to choose one of them. And 1 on this one, again, I need to choose one of them. Or I put 1 on the second one. And in the second case, I put 1 here and 0 here. And then I have, again, 2 solutions. So we have 4 pure strategy denoted by these 4 combinations. So it means put 1 on this and 0 on E, and here we put 1 on F and 0 on Y. So I think it's understood. Now we have to define the payoff for each of them, because the blue payoff was on strategies. So I need to define, let's do it here. And we have a formula. Oh, by the way, I need to say the alpha and beta are between 0 and 1. These are just numbers between 0 and 1. Alpha, beta are between 0 and 1. 2 numbers. So I need to define or to provide a formula U1, 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 and U2, 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 U2 for these 4 strategies, or F, Y, EF, EY, and the same OF, OY, EF. Why? So, and we have a formula. So you have to look at the probability of taking a pass times this. So you look at the formula. It's an exercise just to check why I'm writing these numbers. Minus a beta minus 1. I will explain a bit. But it's always a sum of two terms. If you look carefully, it's a sum of two terms, which is always one of the factors take into account the probability, which is either 0 or 1, and the payoff. So I let you think about how to get these numbers. And then one observation I let you do it is that a Nash equilibrium is OF. But you will observe that something is a bit stupid. Why? Because look, for defining our 4 pure strategies profile, these are profiles. Because I have always, for the first player and for the second player, the first player takes the pass O, the second player takes the pass F, O, Y, E, F, and so on. So these are strategy profile. Why it's a bit stupid? Because I need to define always for the first player and the second player, but if the first player played O, the game is over, right? So it means this definition again doesn't see the dynamics. And the same, no, this one also is meaningless from a point of view of the game. These two are still meaningful. However, if you can check with the definition of Nash equilibrium that this OF is a Nash equilibrium. So you have to check among, you have two conditions to check. But as I said, it's a bit, this is not a natural, it's not a natural strategy profile, behavior strategy profile. It's not a natural behavior strategy profile, because the game is over after the first player, after player 1. So in a sense, I would avoid looking at this Nash equilibrium. I'm wasting my time because it doesn't represent anything. And the first player has no interest in playing this because his payoff would be 0. So he has no interest in going there. He can expect, if he thinks for a while, he has better take this one because he already knows the second player, what would be the best strategy for the second player. The second player has no interest in getting -1. So the second player will, if we are here, will always take the second pass. So it means the first player has no interest in going there, has better go here because he knows that he will get this reward. So I would like, so there is a second observation. There is a second Nash equilibrium, which is precisely EY. Again, you need to check EY is the only meaningful Nash equilibrium. So I did this example first because it's good really to check how to write everything. And then that this definition of Nash equilibrium is not really perfect because we are wasting our time on looking at one Nash equilibrium, which is not meaningful. So we would like directly to get to the second one. And the problem is that this first definition again did not see or did not look at the dynamic. So I want to give a new definition which take into account the dynamics. So it's going to be a new I told you I'm going to look among the set of Nash equilibrium. I'm going to define a new subfamily. But for this, I need to introduce one thing. For any x belonging to the set of vertices, we set f of x, I will make a picture, for the vertex, the set of descendants of x and x itself. So what do I mean by this? You draw a tree, you choose an x, and so what is f of x is, it's a set of vertices first. It is this one, let me click. So it is this one, this one, this one. And what we observe, it's again a tree. It has to be a tree because we are only taking the descendant of x. So I denote by fx for the set of descendant of x and x itself. This is again, so f of x is, it's a bit confusing to say is, but, or defines a new rooted tree. And what is the root? Of course, it's x with root x. So let me do this. Because what is my aim? My aim is to now give a definition of Nash equilibrium or new Nash equilibrium, which take into account that players have to check for the best response or the best Nash equilibrium at every point, not only at the beginning of the game, but at each step in the game. So this is going to be the next idea. But I need one more condition in addition. We say that gamma, so this extensive form game, can be decomposed at x, but it's if no information sets are contain the node. The node is the same as the vertex. And you will see it's perfectly natural in each x defines a subtree, but there is a small problem which I have to avoid. Remember, information set is when, so I need something a bit more complicated. An information set is when two or more vertices are put together. So for this example, X is a not good, because look, if I start with this tree, with this information set made of these 2 points, and if I take this X, one node in this information set belongs to this subtree, and one not. So it means it's a strange, and we have to avoid it. It's a strange information because remember, this information set is when a player doesn't know if he's here or here. So this X is not good because it generates a tree which has only one or part of this. So we say that the X or the initial game can be decomposed at X if we are not in this situation. So for example, here I could take X, I could take this one. This one would be okay. It can be decomposed at this X because now if I draw the subtree, it contains the entire information set. Okay, so that's understandable. So I need this condition of compatibility. Because remember, information set, you cannot distinguish where you are inside the information set. Okay, so now I can give the main definition for this new Nash equilibrium. Or I need just one more thing before. So let gamma be an extensive form game. Which I assume that it can be decomposed at X, a certain point X in V. Of course, I'm not going to decompose at any leaf because a leaf is the endpoint, there is nothing after, so it's not an interesting situation. So I assume that this is the situation. We are in this situation. Then the game obtained by restriction to f of x is called the subgame gamma. So I'm not doing anything special. I'm just saying I start with a game. And a game, remember, is a tree with some information set on blah, blah, blah. Now, if I have an X where the game can be decomposed, I can look just at this restriction. So at this game, this is gamma X. It's a new game. It's a new extensive form game, but starting at X instead of starting at the root. And now you see, all conditions I had on gamma are still valid on gamma X, precisely because I took care of this situation. If I were not in the previous situation, if I considered this, there would be a problem. So I call this subgame gamma X. And the same for a strategy. Remember, a strategy gives me numbers on each edge. So similarly, from a behavior strategy, B in this set, we get a behavior strategy, which I'm going to denote or call BX on gamma x. Because remember, behavior strategy is going to give you some numbers on all edges. Now, if you restrict your attention on part of this figure, you still have a behavior strategy on this subgame. Nothing complicated here. And now we can give a better definition for some Nash equilibrium. Do you have any question? It's a lot of new definitions today, so I encourage you to work on a few examples. Even if the examples are simple, you can learn a lot. So, subgame perfect equilibrium. This is the new name, a subgame perfect equilibrium is a behavior strategy, because it has to be a behavior strategy. B, like this, such that its restriction Bx is a Nash equilibrium. On any subgame gamma x. And if you think about it, it's more clever. Because it means when players are doing the game, okay, they move inside this, suddenly, let's say they reach this point. Oh, each player should think again, what is the best strategy now? And look for the best strategy knowing that they are here. That's why whenever you can decompose the game, you look for a strategy which is a Nash for this subpart. So at each step you do it. The first definition of a Nash equilibrium, you did it only at the beginning. But now, according to where you are, you improve your set of Nash equilibrium. So just an easy observation. This subgame, these subgame perfect equilibrium are among the set of Nash equilibrium. So remark, if you take Nash, then inside you have the perfect, no, subgame perfect. Why is it a subset, subgame perfect? Can you tell me why it's inside? Why it's always inside? Because take X, it has to be satisfy this for all X where it can be decomposed. So in particular, if you choose a root, it has to be a Nash equilibrium at the root, from the root. So that's why it's inside. But it means you eliminate, you disregard all Nash equilibrium which are here. And in the previous example, so in the example I mentioned, in the previous example, the Nash equilibrium, which was the annoying one, it was OF. OF was here. If you check, OF was here, while EF is here. So it means it's a way already to eliminate this by looking at these subgame perfect equilibrium. So it's a refinement. Still, there is a problem. This definition is not perfect. Can you see why? Can you guess why this definition of subgame perfect equilibrium is not sufficient? Because it assumes that you can decompose. But if you have several things like this, maybe you cannot decompose. Because remember, I need this condition about decomposition. If now we have other sets, let's say, okay, no, this graph is too simple, but if you have a more complicated graph with several information sets, you might not be able to decompose. And with this definition, I don't do anything with, I don't, there is nothing on this part, and I would like to put some information on this part. So I want now to take benefit from this. So we are going to see one more thing, which is going to use the information about this information set. So the theory is quite nice because people are trying everything and looking for the best solution. So I want to use now the information here. But before this, I will just give you another thing. Or first, a proposition about this subgame perfect equilibrium. Proposition, so it's in two steps. Every extensive form game with perfect recall, always this condition with perfect recall has a subgame perfect equilibrium. So it's meaningful. Whenever we have perfect recall, at least there exists one. There is in the note, there is a second statement, but I don't need to write it here.
Professor?
Yes.
Sorry, it's just a small thing, but in your diagram, you put OF in the Nash. I think it's OY.
Is it a mistake? Nobody complain. Wait. No, in my notes.
Sorry, EY rather than OF.
Oh yeah, this is EY. Right, thank you. I told you, we miss you. Come back next week.
Definitely.
Thank you. Okay, so the good point is they always exist at least one. There is a second statement, but I don't need it. Okay, I need to introduce one definition which is not directly related to what I'm doing right now, because my next aim, as I said, is going to take advantage of this set. But there is one definition which I could have given before, but let's introduce it now. So it's a general definition for many games. Not only this one you will see for many games. I give it to you now because it already appeared in some reports and you can use it in other reports. It's about dominating strategy. So let A, which is the product I up to N AI, a set of strategy profile and UI, a family of payoff. So you can see you can apply it for both the strategy game and also the what we are studying now is extensive form game, a family of payoff. And I consider AI and AI prime two elements in AI. You know, even Muyan, even if I don't like ChatGPT, I'm always speaking about AI. no relation, but I wanted to attract your attention. Really? Thank you. So I consider 2 points or 2 strategies, and I'm going to say that AI is weakly dominates AI prime if there are 2 conditions. If, so I give a definition of domination, weakly dominates. If there are 2 conditions for any AJ in AJ, J is different from I, we have this U of A1 to AI minus 1, AI plus 1, AN. This is UI. This is bigger or equal to UI of A1, AI minus 1, I prime. So what you observe, it's simply I'm comparing this guy with this one, and all the other one are the same. All strategies for the other players are the same, but I say that one weakly dominates the other one if we have this inequality. And there is a second condition. Now I hope I haven't done any mistakes in the notes. Let's see. There exists a J prime inside B, inside AJ. J different. I. So that now if I look at UI of A1 prime, AI prime minus AI. Maybe the notation is not the best one, but this is bigger or equal to UI at A1. And this one is a strict. So weakly dominates means you always have an inequality or equal, but at least at 1 for 1 other strategy, you have a strict inequality. So again, all these guys are the same, but for one of them, you have a strict inequality. So it means, and you can see why it's interesting, because in a sense you can, if you list all strategies, the AI prime is not really useful because you have one which behaves better, which gives you a better payoff. Okay, and there is a second part in this definition. So we also say that AI prime is weakly dominated by AI. It's just the same thing, is weakly dominated by AI. So this is the first definition. But if there is a weak, there is a second part. So the second part in this definition, if the inequality is strict, so this inequality here, if this inequality is strict, So it means not equal, but strict. Just this. For any A1 prime up to AI, or any A1 to AI minus 1, AI plus 1, AN. In this case, we say that AI strictly dominates AI prime, or AI prime is strictly dominated by AI. That's a natural definition. You can apply it for the second chapter, so for strategic games. You can apply it for these extensive form games, except that probably the name would be slightly different, but the definition is the same. And why I wanted to mention this, because I encourage you to do another set of exercise, which I do not present, but there is one keyword I put in the notes, exercise. And there are many examples on internet, so you can just look at one example, try to understand. Solve extensive form game, form game with backward induction, which is a technique. It's not complicated. It's just one way to solve, so to find the best strategy inductively. So if you haven't done any report, or if you want to understand a little bit, just Google backward induction with game theory. You are going to find plenty of examples on internet, and try to understand how it goes. It's an application. But if you write a report on this, please use our notation. Otherwise, nobody can understand. So I encourage you to look at this. Okay. So we have 5 more. Do you have any question?
Professor, I have a question about backward
Wait,
induction.
I cannot hear you. Wait a second.
Sorry.
Yes, what is your
I
question?
have a question about backward induction. So in this,
yes.
So in this kind of like you start at the leaves of the
Okay,
graph.
please take a while, look carefully on internet, spend half an hour, and then you can ask me your question.
Okay.
No, it's a bit too early. You know, I just mentioned this word, and you're already asking a more precise question. Please take your time and try to make an exercise. So the remark, which I already mentioned it, but I didn't write anything. In the previous definition, no, not this one. In the definition of subgame perfect equilibrium, we assumed that gamma can be decomposed at least in some subgames, can be decomposed at least in some subgames. But as I mentioned, it's not always the case. But if you have too many information set containing several points, or at least 2 points, it might not be possible. But if too many information set contains more than 1 point, it might not be possible. It might not be decomposed. So this is a drawback of the previous definition. And you can easily see one or two examples where you cannot decompose. So it means this definition is not always so useful. But as I said, I want to take advantage of this thing. So I'm going to introduce one new information. So the new idea, and I will just finish with one or two sentences about this new idea. At information set containing more than one point, at information set containing more than one point and one vertex, we are going to believe in something. We will add beliefs. Because remember, what are these information sets with more than one node? It's when you don't know where you are. I define these information set as vertices where you don't know because there is a lack of information if you are at this one or at this one. So now if you add an information, you believe that for 60, there is 60% of chance that you are here and only 40% that you are here. If you have a good reason to put these numbers, you are adding some information. Because then if you have, let's say, 60% here and only 40% here, it means what happens here, you have a better chance to reach this part compared to this part. So this is what I will call, or what is called beliefs. We are going to put some probability on these points. But of course, there are different ways to do it. But the next step is first to define what is a belief, and then find a way to, at least one way to put some meaningful numbers. So this is what we are going to do next week. And I guess so far we will use this information more than just next time, but again in the future. If you have a partial information, you can add this information in your information set. So I will come back to this. And we will do it according to Bayes' rule. We'll explain. Okay, any question or remark? So it was a bit dense because we had to deal with many things, but probably next time we are going already to finish this chapter on extensive games. But what is important to remember is at least you know how to solve them for perfect recall because we have this algorithm for the first part for strategic games. But there is a second approach, which is with this backward induction, and I encourage you to look at some examples. Okay. And Hevido, thank you for writing a report on backward induction. Okay, so see you next week. The list with names. Thank you. So see you next week, and if you have any question, you can always send me a message.
Okay, thank you, Professor.
Thank you. Goodbye.